of the class from Wednesday, the 23rd of March. So, started up at the top, went down through this one more time, but by now you've got it surely, and hovered over each of these three terms. Traveling salesman problem, which by now hopefully you get what it is. The fact that computational optimization is a subset of algorithms that come up with an optimal solution, if not and usually not the definitive solution. And computationally intractable being a good adjective for problems which you just can't use a computer for practically to come up with a definitive answer, because it would just take too long. And the traveling salesman problem is one of those. And we went through fairly slowly the first part of the case study here, but I think you can go through it and understand it yourselves for this review video. Just the whole point that if you have a tour of 20 cities, 20 towns, 20 places, good luck finding the optimal solution, because you won't. There's just not enough time to do it brute force through that many combinations, because we just don't have that much time. So there's got to be some other way. And there are other ways to come up with optimal, if not perfect, solutions. And these optimal but not perfect solutions are referred to as heuristics. So genetic algorithms are one heuristic approach to the traveling salesman problem. And just the other underlined, hover over. Definition is tour. The tour is just a valid progression through the towns or cities in a particular traveling salesman problem, meaning that you go through each of the towns once and only once, returning to where you started. So we started by taking a look, this class, at not the advantages and disadvantages of genetic algorithms, but the other approaches in comparison to genetic algorithms. And so, better talk about the special note. This challenge number 4 of 4 challenges is divided up into 2 parts. The first part is the alternative approaches, and the second part is the more important part, where when we've done 2 or 3 days of this, you'll appreciate the advantages of genetic algorithms over these other approaches. But it's a good little thing to have done this first class, to have gone over some other approaches. You want to come up with a tour that goes through a certain number of cities in the shortest route possible. You can try to do a brute force, but it just won't work. Up to around 10 towns. 10 towns or 1.5 million different permutations you could probably find a computer to do. But anything above that, you won't. Same thing with passwords, and that's what we talked about in class, how if you have a password of 20 out of 26 letters and you do the calculation, 26 to the power of 6, you come up with around 300 million. Could a computer test brute force wise 300 million passwords? Yeah, might take a little while, but yeah, so don't make your password just letters and 6 letters long. You get brute force, I think. Another approach to the traveling salesman problem is the mathematical integer linear programming formulations approach. And if you're into this, great, but most people aren't. For starters, furthermore, it doesn't come up necessarily with the definitive solution, and it takes a lot of time. But there are mathematical linear programming approaches to the traveling salesman problem. And then there are other heuristic approaches. The first one that we looked at in class is the ant colony one, which is cool, and I'll leave it at that. You can take a look and see if you can follow through the iterations to see what's going on in terms of the pheromones left and so on. And you can go even further, but you don't need to. You just basically need to appreciate that there are other alternatives, basically being able to list off what those other alternatives are and say a thing or two about them. The most classic approach to the traveling salesman problem is the nearest neighbor approach. And if you watch this video, you'll get it. It makes sense. You just start wherever you start, and you look for the nearest neighbor. And from that nearest neighbor, you look for the nearest neighbor from it, and so on and so on and so on. It'll come up with a heuristic, pretty good solution. Even better is a two-op swap. Take a look at the video, play it. You're going to see how it works. Basically, you kind of have to play it a little bit to show you, to talk about it. Basically, what it does, if we go back a couple of steps and pause it, is it looks for, well, it doesn't necessarily look for crossovers, or crossovers are basically things that need to be corrected. Basically, it just swaps a couple of different edges and recalculates the total path, and if the total path, having made that change, is better, it keeps that switch, and it moves on and it finds a couple other random points to swap, and it sees if we swap those edges, if there's an improvement, we keep that improvement as well. And it does actually work pretty well. Probably not as good as a good genetic algorithm, though. The whole deal with genetic algorithms, though, is that you've really got to fine-tune them, and we're going to get to that in the next few days. But there you go. There are, and then we get into the actual advantages. So there are other approaches to the traveling salesman problem. 3 heuristic are listed here, along with the mathematical and brute force. So then we went back and revisited this simple outline of what a genetic algorithm is, the whole idea of initializing a population of a whole bunch of different random tours, and then looping through, and each time basically evaluating to see if you've reached the basic, I mean, there are other evaluations, there are other termination conditions, but basically seeing if you've solved the problem. Have you got below a certain number of kilometers? And when you've got a tour that's below a certain number of kilometers, you break, you're finished. Otherwise, you select, which is selecting a subset of a particular generation, usually the best chromosomes, but not necessarily, crossing them over, in other words, mating them, and mutating them a little bit, anyway, to try to come up with novel solutions, and repeating this process. And so in class, I went over a little bit more slowly than I'll go over now, the whole idea of initialization of the population. That's just one, you want 100 or so. Evaluation, really easy in this case, because all we need to do is find out what the distance is between F and J, and the distance between J and G, and so on, and count up all the different distances, add them up, and we get ourselves a fitness. The fitness function is simply, for us, the traveling salesman problem, add up the total distance covered. And generally, we're going to want to rank those from the shortest to the longest. And I think you pretty well get that, and we went over a little bit more detail, but you can slow down if you need to at this point. But what we got into, though, was one of the 4 challenges that details what roulette wheel selection, what the different kinds of selection techniques are. So again, the idea is that you initialize population, you evaluate it, and then from that population, you're going to select certain individuals to breed. And generally, the individuals you're going to select to breed are going to be the better individuals, the better chromosomes, the shorter roots, but not necessarily. And you know what? I skipped something. That's why, not necessarily, is why we just briefly went to convergence, because you can't just take the best and cross them over with the best, and then take the best of those and cross them over with the best, because it doesn't work optimally. You need to throw in, and I really didn't get into this in class, and so I won't right now. You really do need to throw in variation, diversity. Diversity is the key, diversity is the key, diversity. You know, not completely diverse, but you need a little bit of spice thrown in to come up with novel solutions. So back to that on day 4 of this, but for now, just keep in mind that when we're taking these selection techniques, or choosing these selection techniques, we're doing so with that in mind, with the fact that you don't just want to take the best with the best. It just doesn't, nature doesn't work that way, and genetic algorithms don't work that way. They kind of do to a point, to an optimal minima or an optimal maxima, but the optimal minima or the optimal maxima is not the absolute, or even as close to the absolute as you can get if you throw in these other spicy things. So That's a good way of looking at it, is that we're throwing in a little bit of spice with each one of these, except for truncation. Truncation is just plain old, just take the top one. So we'll take a look at all these right now through this link. And there wasn't enough time to go through all this, and so we'll go over it again next class on Friday. But basically, let's just start with the easiest. After you've got your population of 100, I only did 10 here because 10's enough to get the idea that these are just randomly generated, and we come up with the scores, which is basically the distance. And then we're going to rank them. You pretty well always do rank them. And in the case of truncation, which is the fourth of the 4 selection techniques mentioned, you just truncate. You just pick a certain number of the top, and you keep them, and all the others you ditch. And so we could ditch the bottom 50%, keep the top 50%, and use the top 50% for breeding of the next generation. And we'll do pretty well with that because we're taking good roots, mixing them with good roots, and we're going to get good roots. And by roots, I mean tours. So, but we're missing the spice. We're missing the little bits of these tours down here that might just get us closer to that absolute optimum. But just to go down to where the notes are, and again, I'll have to do this again on Friday because we just rushed through this, and this is rushing through just because it's a summary video, but there you go. So we took the number 1, number 2, number 3, number 4, number 5. Those will be the population, that is the population that will be used for crossing with each other and coming up with the next generation. And it wouldn't be 5, it'd be 50 or 500. It wouldn't be a population like 5, but that just fits the diagram that I'm using here. So that's the fourth of the 4 selection techniques. You just take the best. And then we get to the more interesting one, starting with roulette wheel selection. Roulette wheel selection takes the top 5 or the top 50. It's not going to be 5, but it works for the diagram. So, but this is what we're doing. We've got 10, so we'll take the top 5. So we rank them, take the top 5. 9, 2, 2, pretty good, all the way to 2, 3, 2, 2. And you're going to notice just in looking at these numbers that these two are pretty good and pretty close to each other. And there's a huge jump, almost double, to these other 3 that we're going to take. So what you end up doing, mathematically, pretty easy to code, is you say the 1 and the 2 get the biggest piece of the roulette wheel, right? Because they're the best solutions by quite a bit. And then those other top 5 aren't that good, but they get a bit of the roulette wheel. So we spin the roulette wheel, and we spin it, we spin it, and we spin it, and we spin it. We come up with another population of, say, 50 or 100. And you know, a lot of them are going to be this 1. You can't cross with yourself, but you can cross with the 2. The 1 can cross with the 2. So, and the 1 can cross with the 4 and 3. So you spin the roulette wheel, and you're usually going to come up with the best because they're weighted. But the problem is, and I could get to my iPad and draw this out like I drew it on the board, but I think I'll just try to explain it, that the problem is that sooner or later, as you go through these generations, you're going to have dominance. You're going to have the monopoly effect of, in this case, 2 chromosomes are really going to basically take over, and you're going to lose the diversity. So a better approach, slightly better, and again, we're going to go over this a little bit more slowly on Friday, but a little bit better approach is the stochastic universal sampling. Stochastic means random, universal means everything's got a better chance. And everything's got a chance up here, by the way. You know, the first few iterations, you're going to get a few 5s, but you're going to get way more 1s and 2s that are just going to take over the whole process. And so with the stochastic universal sampling method, you have 2 pointers. So it's Wheel of Fortune with two winners, as it were, right? You can have this selection point, and 38% of the time, it's going to come up with number 1. But when it comes up with number 1, it's also going to come up with something on the other side. And this is where this is an imperfect, it's not imperfect, it's just not the best example. A better example would be this divided up into more slivers. But basically, whenever the dominant one is selected, another one will be selected. So it's easier to see over here when we have 3 more selection points, not just the regular old Wheel of Fortune selection point, but 3 others. And so if there's 1 here, and there's 1 here, and there's 1 here, when it lands on number 1, well, actually, number 2 gets twice as many chances, or twice as many chromosomes sent to the next breeding generation, and so does this weakest of all, right? And again, I almost feel like going into Photoshop and fixing this up a little bit, but imagine this being slivered even further. So then when this dominant one, every time this dominant one gets chosen, which is almost half the time, you're going to have others that enter into the race as well. Yeah, so it's going to be a little bit slower, but it's going to explore, as we get into this over the next couple of days, you're going to explore the fitness landscape a little bit more than just the regular old roulette wheel with one pointer. So it's good. And we'll talk about why it's good and why it's not so good, the advantages in evaluating this on Friday. And then the one that we just barely got to, which may be the best overall, the more that I think about it, but the way that it works is there's a tournament. In fact, there's a bunch of tournaments. So what you do is you go up to, and I didn't have a lot of time for this one, so I hope a bunch of you are watching this that even were at the class, that what you're going to do is take them not sorted, but take them unsorted. Take your 100 or your 200 or your 500 unsorted and make tournaments. And in this case, it just makes sense to make maybe tournaments of 3, but if you had 100, make tournaments of 20. So, but if we did a tournament of 3 up here, remember this is random now, 1, 2, 3, 4, 5. If we go random, then 3, 3, and it'll have to be 4 because there are 10 of these. So the winner here is going to be this shortest tour, which is this one. And then the winner here is going to be definitely that one. And then the winner here is going to be definitely that one. So the two that would have come up, number 1 and number 2 that would have come up anyway, are going to be used for the next generation. But so is is the 5th. This was unlikely. We would have expected number 1, number 2, and number 3 if we were just picking 3, right? Not number 1, number 2, and number 5. But again, take this out to a bigger number. So we're going to end up with most of the top 50 of 100. And we're going to end up with a scattering of others, and that will throw in the diversity. So tournaments, well, they're my favorite at this point, because I just think it'd be interesting to tweak our program that we do have, and I don't even know which selection technique it's using. I don't know if I can tell right now. I haven't looked at it yet, but you can download this. It's on the website and try to figure out. Well, let's just take a look really quickly, see if I can figure this out on the spot. Selection, which one is it using? 1 in 5 chances of finding the fittest. Okay. Pass around is going to get a little bit, it's probably a little bit much, but it's not that much to it. Odds of not picking the fittest. This is, okay, this is the first time I've looked at this, but basically all this looks like it's doing is kind of like a roulette wheel where it's just picking some non-fittest. It's picking mainly the fittest. I think, again, this is the first time I've looked at this, first minute I've looked at this, but I think it's picking basically the fittest and putting them into a chromosome array list, but it's also just randomly throwing in a bit of spice. So I'll look at that another time and try to figure it out, but it's not tournament selection per se. It's more like a roulette wheel, I would say at this point, but we'll look at it later. But yeah, so just look through this. Don't look through this. Just appreciate, you know how tournaments work, right? And this is what I said in class, and I think I should add it to the notes because it would make sense to you that you have divisions, right? If I'm doing the NHL, you got the Eastern, the Western, and the Pacific, whatever divisions, and okay, your team that you don't like is at the top of the Pacific Division. What are you going to say? You're going to say, yeah, but they're in a bad division anyway, right? They're gonna lose out when they get to the playoffs and the Stanley Cup Finals, or not. They're at the top of their division for a reason, so you never know. And so I like this approach. I do. The top ones, I'm going to wrap this up right now. The top ones are going to make it. They're definitely going to make it, but you're going to get a random array of non-top 50, if that's the way that you're going. And that's a nice way to throw in a little bit of randomness. So more on that, I've already said this 4 times, but more on all of this at the beginning of the class on Friday.